Okay, so we did the G loading, we have the masses. So now let's do a modal analysis on this. So I'm going to do a unconstrained modal analysis on this, like I asked you to do for the project. Okay, so we will not use these SPCs. I'll turn them off visually, but it really doesn't matter. But we'll keep, just so you kind of are good with it. So I'll turn them off by clicking on the little FEA thing next to them, so they're gone. But it really doesn't matter. I got these node numbers. Let's turn off the node numbers. Okay, so I'm going to go back to tools, numbers, nodes, off, and there they go. Okay? Okay, so let's do the modal analysis, right? So remember, the modal analysis is a different type of solution method. It's a normal modes analysis. It's not a linear static analysis. And we also will need to create a load collector that has the solution parameters for the eigenvalue solver that will extract the natural modes and the natural frequencies, okay? So we're going to do that. We're going to make another load collector. So right-click in the little model window, create new load collector. I'm going to call this modal parameters or modal solution. And it's going to be we're going to change the card image. Remember, we're going to use this real valued eigenvalue solution using this Langsos method. So that is the EIGRL thing, EIGRL, whatever you want to call it. And that's what it is. So we're going to do unconstrained, which means, right, we're going to have the all six rigid body modes, which will have a natural frequency of 0. So I'm not interested in those at all. So I'm going to set the lower bound here to 0.1 hertz, okay? So I won't see those, unless there's some weird numerical round off that bumps us up, but usually won't see those. And let's look at the first 10 modes. So ND changes the number of modes you solve for. So that's what it's going to do, okay? Mass scaling is fine. You can leave everything else the same, right? If you want to cap, if you don't want to see any modes greater than 1,000 hertz, you could put 1,000 in for V2, but that's fine the way it is now. So we're good. So there I've got the modal solution parameters defined. Now I just have to do the load step. So I'm going to make a new load step. So now, we had the 3 load steps for the G analysis. So now I'm going to have a 4th load step, which is for the modal analysis. So again, we're going to right click in here, create load step. And this is going to be the modal, so I'll call it modal. And the analysis type now is going to be normal modes. So that's all. It's up top, close, but a couple below linear static. So now we're going to do a modal analysis. There's no SPCs, so I'm going to leave that undefined. But I do have to specify the solution method structural, and that's going to be picking that modal solution load collector I just made. All right, so now we're good. So now it's going to figure out the natural frequency of this. There's no forces in a natural frequency analysis. It's just free vibration, okay? And it's going to have the masses in there, and we're going to see the non-zero natural frequencies, the first 10 of them, okay? So we're ready to go. So let's see if we can save this. And now let's do the analysis again. Optistruct, and we're going to run this. It's going to write over the old one. And this shouldn't take so long. It takes a little longer to do the modal analysis. So if you have a lot of elements, you guys might see a little bit of time for the modal analysis, but you can see for this one, it spends more time just kind of opening and closing things and actually doing the simulation. So there it is. It ran fine. So let's look at the results now. All right. So let's put this in the orientation we want it, right? What was it? It looks like this. That's kind of like the picture we had in Hypermesh. And now you can see we have those 3 subcases for the G loading we did previously, but now we have a 4th subcase, which is the modal analysis. So let's click on that. And one thing you'll notice is Immediately below that subcase bar, there's another bar here. And this shows you can then now, like, do I want to see the first mode, the second mode, the third mode, so on and so forth. So the first mode here is 65.5 hertz, because that's what F is, right? So let's look at that. And we'll change the animation to be like a modal type of animation. There's this deformed mode shape. We can like let it go. And that makes sense. That's the lowest mode. So our structure vibrates like that at 65.5 hertz. Okay? Now we can change that to look at the second mode. So the second mode's a little bit more than that. It's 66.2 hertz, and I'm going to almost guarantee, due to symmetry, it's going to be looking the same but vibrating in the X direction. And so there it is. It's almost the same frequency because it's almost the same thing going on. So those are two bending modes, right? Just in different planes. And probably the third one. Okay, so the third one here, which is at 74.8.9 hertz, is a bit of a twisting one, right? And then let's look at the fourth one, which is the fourth one's at 95.7 hertz. It's bending, but you can see it's like a second order bending. And we can keep going from there. There's another twist mode at 97 hertz. It's pretty similar to the other one, right? That's close. You can see the mode shifts. Different frequency though. And then let's go to this one. This is a 100 hertz. It's a bending, but you know, it's got this little shear kick in there. And, oh, okay, there's a much different mode. So this is like a shearing mode with a little bit of bending, right? But you can see that one is quite a bit higher. So before we were at like 100 hertz. Now we are at like 150 hertz, right? Oh, sorry, the other ones were like at 10. I'm sorry, I was misreading those. I'm sorry. This is like 6 hertz. This one is like 10 hertz. And then we jump all the way up here. Wait, that one's 100 hertz. And then like this one is 150 hertz. And then if we go really high, I don't know if the correct data on this one, let's look at the 10th mode. You can see they just start to get, they still look like torsional and bending ones, but they kind of have little different shapes to them, right? And you'll see much more complexity. Like if we solve even more modes, you would see that they become like higher order modes, okay? But actually that's still a pretty good fundamental structural mode. So I don't know, I might be tempted to look at more modes, but anyway. But that's the modal analysis. Now, you can't see stresses and you can't see displacements because, you know, this is a free vibration problem. So the only way you could know how much it's vibrating or deforming and then the resultant stresses is to say, like, we have some initial conditions. Like, we drop, you know, we initially move these points, you know, we displace the end and let it ring or something like that, right? Like, here's the structure, and we kind of pull it down a little bit and let it vibrate. You know what I mean? That's a forced vibration problem. That's a vibration problem with an initial condition. Still a free vibration problem. But if we were to set that up, it's a different type of analysis. You would see stresses and displacements, but only because we've defined that initial condition. In this analysis, we have not defined that initial condition, okay? So as I was saying, like in class, like if we look at this first mode here, it's a bending one. So if we want to stiffen up the structure, like one thing I might be tempted to do is actually stiffen up these top and bottom frame elements, maybe make them a bigger eye, like a different section, right? And then see what happens, okay? All right. I think that's enough for that. We'll stop.